So if the network and the projectors hold out, we can have this two-screen experience. Here's the thing I want you to learn how to do, and there's an online exercise about it. Last time we looked at how to turn an assembly language program into machine code, and today we're going to figure out how to go in the other direction. So you can see in my box, I've just got a load of hexadecimal digits, which might well be a program, if we're lucky. So let's see if we can use our powers of logical deduction to figure out what the program is. Because if we can figure out what the program is, then we might figure out what it does without having to go through the whole dreary business of running it. So let's see. What we have is one clue so far. It's pretty clear that we're going to start running this program at the start, which means that, you see that first 6 there? That's probably going to be the code for some sort of instruction. So, if that 6 is a code for an instruction, what instruction is it? It's get. Tell you what we can do. We can delete the 6 and write get, put the rest of the stuff on a new line. I'll press send. Okay. Now we know that after get executes, we've got, it's going to go through to the next instruction, yeah? So that tells us that the next thing in the memory after the get is probably also code. So we've got a code clue for location 1. So what's in location 1 will be that 3. So if that's the beginning of an instruction, what would the instruction be? Jump if not 0. So we delete the 3 and we write jump if not 0. Okay, does it have an operand? Yes. And that operand is going to be this 9. So what we ought to do is count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This 4 here, that's the thing that's at location 9. Let's give it a label. And as we might jump to it, that's a pretty good clue that what's at this label is code. So let's just label it code. We put a label in there, I'll actually whack it down below. And then I'll change the 9 to say code. And then I'll hit send again. And we're making some progress. And you can see all the time, the contents of the box always assemble to the same sequence of hexadecimal digits that we started. But gradually, as we get more clues for where the code is, we're turning more and more of it into instructions rather than just raw data. So that's the game. This game is called Disassembling. Conditional jump instructions are absolute, you get a double bonus for a conditional jump instruction because you know that wherever the operand gives you a code clue because you might jump to it, but also you might not jump. So you also have a code clue for what's immediately afterwards. That's to say, we have a code clue for this 4. So if this 4 is the beginning of an instruction, what is it? It's LDA, load the accumulator. Now, does it take an operand? Yes, it does. And that operand is currently 7, so we better give location 7 a label. Now, this code was location 9, so this 0 here is the one at location 7. I'm just going to give it a label X. Right, because we're loading it into the accumulator, so I changed this 7 to an X, because it's the operand. I just labeled location 7 so I could give the LDA a label as its operand. this, see if we're still in good shape. Yep, that's good. Yeah, so when you see a load instruction or a store instruction or even an add with carry that takes an operand, that's a good clue that the operand is data rather than code. Unless it's a weird self-modifying program, of course. But at the moment, given that we're loading the contents of location X into the accumulator, that's a pretty good clue that we should consider that location to store data rather than code. Meanwhile, what about that next 7 after the LEAX? Would that be code or data?
Code.
That's going to be code because after we've executed that load accumulator instruction, we're going to end up there. Well, since it's code, what is it? It's the put instruction. And does that give us a code clue? Yeah, well, after we've executed the put instruction, we'll carry on. So we've got a good code clue for that 0. Since we've got a code clue for the 0, what do we think it is? Halt. Now, does halt give us a code clue? No, it doesn't, because the one thing we're pretty sure of is that we're not going to carry on executing after the halt instruction. So once we reach halt, we've got no more clues. But hang on a minute, we still had a code clue from our conditional jump instruction. So we're not done yet. We've got a code clue for this 4. So if that's code, what instruction is it? It's load accumulator, and its operand is 7, which we already called X. So we're fine. Have we still got a code clue? Well, yeah, we have. You can see the machine is helping. So we think this C is code. What is it? Set carry flag. And that means we probably think this A is code as well. Now what do we have? Add with carry. So this 8 needs a label. That's where that 0 is. I'm going to call it Z. And then replace the 8 by the Z. Let's see if we're alright so far. Okay. And have we got any more code clues? Well, yeah, because after the add with carry, we'll move on to that 5. So what's the 5?
Store accumulator.
It's store accumulator. And again, we're using 7 as an operand. And that was the thing we called X. So that's the whole of the program. So the game is make use of code clues to translate little bits of memory into instructions, and then see what code clues and what data clues you get from that instruction. Quite often, you'll get a code clue for the next instruction. And if you've got a load or a store or an add with carry, you've got a data clue for the operand. And then what you do is you turn everything that you've got code clues for into instructions, and everything that you've got data clues for, you label it, but you leave it alone. So now we've got a program. You'll notice, by the way, this store accumulator instruction is at the end of memory. What happens after it gets executed? Yeah, we loop back round to the start. And this is a trick which allows you to create a loop in a tiny program without spending memory on a jump instruction. And since there really isn't very much memory in the tiny machine, it's a good trick to be able to create a loop without using a jump instruction. And so you can see what we have here is the beginning of a loop at the beginning of memory, and then something which might jump to the code at the end of memory. But if we don't jump, we carry on and finish off with this halt instruction. And then we've got a data block in the middle. Now, we can not only deduce from this what the program is, which we've successfully done, but experienced tiny experts can tell you exactly who wrote this program, because this is the coding style of a programmer called Biffo. You'll probably encounter Biffo quite a lot in the weeks to come. Biffo always likes to do this trick of making the program fit into memory so he gets a loop for free and putting the data block in the middle. That's Biffo's trademark, or one of them. And the other trademark is that he always likes to see what happens if you put in the input B1FF05 or Biffos. I don't know, I'll give you a couple of minutes to think about that. If the input is B1FF05, what's the output? Take a couple of minutes and have a think about that. If you need it, anyone, I've got some spare tiny guides if they'd be useful, but you've got one up there, but you've got one up there. You have as long as it takes me to write the program on a piece of paper. Anyone want to guess the output? Any other guesses? B. You're not winning. 4. Let's see why. Better zoom out a little. Okay. So that's our program. And the input was, the input is B1FF05. Yeah? Okay. How do we go about this? Well, a good thing to do once you've got the program is to just draw arrows for the flow of controls. So this conditional jump if not 0 to code, it might jump to there. And then we might, if we get to here, we loop back round to the beginning. So we can see what's going on. There's a loop in the code, but and we'll keep going round that loop as long as this jump if not 0 jumps. If this doesn't jump, then we'll run this last bit of code, load what's in X, send it to the output, and stop. Okay? So the question is, so the output is going to be whatever is in X by the time we stop looping. Does everybody see that? So now we've got to figure out what this loop is doing to x and how this loop actually works. What's in x when we start? 0. You can see that, it's there. Okay. Next thing we need to think about is how this jump if not 0 works. Which instruction is controlling the 0 flag for that jump? I hear an ADC. Any other takers? Did I hear a get? I thought I did. Maybe it's just wishful thinking. You know, you can see that the get instruction does indeed monkey with the 0 flag. Yeah? So what you need to do when you see this conditional jump if 0 or jump if not 0, is to look backwards from it in the code to see what is the last thing before that instruction that messes with the 0 flag. And we could see that get is, I don't know what he's written. Nothing. I don't consider that attendance. He's free to go, but he's not free to be counted as being here. Anyway, let's maybe he is. He's been B for half a lecture. I'll count it. I'll put it back in the box. Right. Okay, so tell me when that jump jumps.
If the first is taken to the input Q is 0, there's
Well,
not 0.
If the input is not 0. Okay, so we're going to keep round the loop as long as we keep getting inputs that aren't 0. Now we've just figured out how far through the input we're going to get. We're going to keep going around the input as long as we get B1FF, but the one that makes us stop is the 0. Does everybody see that? How we figured that out? You look back from the jump if not 0 to the thing that's controlling the 0 flag. And then you think, what's that doing to the 0 flag and why? So that will set the 0 flag if the get receives a 0. So the first 4 times round we don't get a 0, so the 0 flag is clear. 5th time round we'll get a 0. Alright, so we figured out when the loop stops. Now we have to figure out, looking down here, what does the loop do? It adds 1 to x. Let's figure out why. I'm glad I didn't make y one of the variables. So first of all, we load the current value of x into the accumulator. So that means if we're going to do an add in a moment, one of the things we'll be adding is the current value of x. Next, we set the carry flag. And that means that one of the things we'll be adding is a 1. And then we do ADC Z. What is currently stored in Z? 0. And do we ever store anything to Z? No. So Z is going to stay 0. So we load the current value of x, and we add a 1 from the carry flag and a 0 from location Z. That'll give us x plus 1 in the accumulator. And then we store that to x. So we overwrite the old value of x with x plus 1. So that means we've added 1 to the value of x. And we do that each time we go around the loop. We figured out that we go around the loop 4 times. and x starts at 0, and we go around 4 times, and each time we add 1 to x, what does x end up being? 4. And then the loop, once we're out of the loop, we load the value of x, that will be 4, we send it to the output, and then we halt. So the output is indeed 4. Let's see if the machine agrees. Yes, it does. Okay. Everybody happy with that? Remember, find the loop structure, so trace where the jump instructions take you, and remember that you can have a loop just by looping around from the end of memory to the start. And then when you have conditional jumps, figure out what is monkeying with the 0 flag. That's the game. Okay.